All right, get ready for a wild one. Today we're diving into the world of quantum physics. Yeah, it might sound intimidating, but trust me, we're going to bring it down and make it, well, if not exactly easy, at least totally fascinating.
Definitely fascinating. We're working with a beginner's guide, your quantum physics superpower, which does a great job laying out this mind-bending feel.
Mind-bending is a good way to put it.
Yeah.
So when we talk about quantum physics, what are we actually talking about?
Okay, so think of it like this. You've got the world we see and interact with every day, right? That's where classical physics reigns supreme, the laws of motion, gravity, all that good stuff. But then imagine you've got this super-powered microscope, and you zoom in way past cells, past molecules, all the way down to the tiniest particles imaginable.
Okay, getting seriously small now.
Exactly. And that's where classical physics starts to kind of break down. It's like trying to use a telescope to look at something microscopic just doesn't work. At that subatomic level, a whole new set of rules kicks in, and that's quantum physics, the science of the unbelievably small, where energy isn't smooth and continuous, it's more like chunky.
Chunky energy? All right, now you have to explain that one.
Well, think of it like this. In the classical world, energy is like a ramp. You can be anywhere along its smooth incline. But in the quantum world, it's like a staircase. You can only be on one step or another, no in between.
So energy comes in these little packets.
Exactly. Those are our quanta. And what's even crazier is that these particles, well, they don't really behave like anything we can picture in our heads. They're not little billiard balls whizzing around. Sometimes they act like waves, sometimes particles. It's like they haven't quite made up their minds.
A particle that can't decide what it is.
Yeah.
Okay, this is where my brain usually checks out. But you mentioned something about a superpowered microscope. Is that how scientists actually see this stuff?
Well, we have incredibly powerful microscopes, yes, but even those have limitations. A lot of quantum physics comes down to math, equations that describe the probabilities of where a particle might be or how it might behave. And this isn't exactly new stuff either. Back in 1927, there was this famous gathering of physicists, the Solvay Conference, and they were already wrestling with these mind-blowing concepts.
Oh yeah, I've heard about that. Wasn't Einstein there?
Front and center.
Yeah.
And let's just say he wasn't exactly thrilled with the implications of quantum physics. He famously said, God does not play dice with the universe. Because the idea that things might be fundamentally random, well, it just didn't sit well with him.
So Einstein was team predictable universe,
Hmm.
and everyone else was like, hold my beer, things are about to get weird.
Pretty much. But while the math was there, figuring out how to visualize and make sense of this new quantum reality, that was a challenge. Then came along Richard Feynman in the 40s and 50s, and he changed the game.
Feynman, wasn't he the one with the bongo drums?
The one and only. Besides being a total character, Feynman was a genius at taking incredibly complex ideas and making them understandable. He came up with these things called Feynman diagrams, which at their core were like little doodles that represented particle interactions.
Doodles. For quantum physics, that seems a little too easy.
Don't let the simplicity fool you. These diagrams revolutionized how we understand and work with quantum physics. They were like a visual language that helped make sense of all the craziness happening at the subatomic level. And trust me, there's a lot of craziness to unpack.
All right, lay some of that craziness on me. If classical physics is like our trusty car for navigating the world, what happens when that car tries to take a quantum off-road adventure?
Let's just say you're going to need a whole new vehicle.
All right, so classical physics breaks down. What kind of wild ride are we in for when our metaphorical car crashes and we have to continue on foot?
Well, imagine stepping out of the wreckage and the landscape is like nothing you've ever seen. That's quantum. One of the first things you'd encounter is this thing called wave-particle duality.
Wave-particle duality. That sounds like the name of a bad sci-fi movie.
Oh, it's way more exciting than that. Picture this. We're used to thinking of things as either waves, like sound waves, or particles, like tiny little marbles.
Makes sense, solid objects versus, vibrations and energy.
Right, but at the quantum level, those categories get all blurry. It's like discovering that an apple can also be a sound wave, depending on how you look at it. Particles, like electrons, they can act like particles or waves, depending on the situation.
Hold on, are you saying it's like morphing back and forth?
It's even weirder than that. It's not that it's switching between states. It's more like it exists in this fuzzy, undefined state of being both until we try to measure it.
So it's only when we try to observe it that it's forced to pick a side.
You got it. That's the observer effect. And it's one of the most mind-blowing things about the quantum world. The act of observing something actually influences how it behaves.
Okay, now that just seems unfair, like the universe is messing with us.
The universe loves to keep us on our toes. Think of it this way. Imagine a spinning coin. Until it lands, it's both heads and tails at the same time, right?
Yeah, okay, I get that.
So an electron, before we measure it, is kind of like that spinning coin. It's in a superposition of states, both wave-like and particle-like. But the moment we try to observe it, to force it to land, so to speak, it collapses into one state or the other.
So we're not just passively observing the quantum world, we're actively participating in shaping it.
Exactly. And this isn't just some theoretical mind game. This wave-particle duality is what makes things like electron microscopes possible.
Those super powerful microscopes that can see things even smaller than atoms.
The very same. They use the wave-like properties of electrons to create images with incredibly high resolution. We're talking about seeing the structure of molecules and even individual atoms.
So in a way, we're using quantum weirdness to explore the quantum world.
We're embracing the weirdness. Because without it, we'd be stuck with our old limited view of how reality works. And trust me, it gets even weirder. Have you heard of quantum entanglement?
Entanglement. Is that anything like getting stuck in a quantum spider web?
Huh, not quite. Although, it can feel just as tangled. Okay, imagine two particles, right? They're linked, not physically, but in this way that transcends distance. You do something to one particle, anything at all, and instantaneously the other particle reacts.
Instantly, like faster than the speed of light.
You got it. We're not talking about sending a signal through space. This is something else entirely. It's as if they are two parts of the same whole, connected across the vastness of space in a way we can barely wrap our heads around.
Okay, now that's just spooky.
Even Einstein thought so. He called it spooky action at a distance. And the thing is, we still don't fully understand how it works, but we know it does work.
All right, so what can we do with these spooky entangled particles? Besides, freaking ourselves out.
Oh, we can do some pretty amazing things. For starters, entanglement is the backbone of quantum computing.
Quantum computing, that's where things get really futuristic, right?
It's the future knocking on our door. You see, classical computers, the ones we use every day, they store information as bits, which are either a 0 or a 1. But quantum computers use qubits, which, thanks to this whole superposition thing we talked about, can be in both states at the same time.
So each qubit is like that spinning coin, both possibilities at once.
Exactly. And this ability to be in multiple states simultaneously gives quantum computers an insane advantage when it comes to certain types of calculations. It's like being able to explore every possible solution path at the same time rather than having to try them one by one.
Sounds powerful. But where does entanglement fit into all of this?
Entanglement is the key to connecting these qubits, creating a network of entangled processors that can work together in ways we're only beginning to understand.
So it's not just about individual qubits being powerful. It's about linking them together in this spooky quantum web.
You've got it. And that's where the true magic of quantum computing lies. And this is just one application. There's quantum cryptography, which uses entanglement to create virtually unbreakable codes, and even quantum teleportation.
Hold up, did you just say teleportation? Like beaming ourselves up, Star Trek style?
Well, not exactly, at least not yet. But we are able to teleport information using entangled particles.
Okay, I think I need a moment to process all of this. We're talking about harnessing the power of the universe's weirdness to do things that seem straight out of science fiction.
And we're just getting started. There are so many potential applications of quantum technologies, everything from revolutionizing medicine to developing new materials and forms of energy. It's an incredibly exciting time to be exploring the quantum world.
Exciting, yes, but also a little terrifying. I mean, this is powerful stuff we're dealing with. What are the ethical considerations we need to keep in mind as we delve deeper into the quantum realm? Yeah, it's a lot to wrap your head around. We've gone from chunky energy to spooky action at a distance. Where do we even go from here? What are the real-world implications of all this quantum weirdness?
That's the question, isn't it? It's easy to get lost in the theoretical weeds, but quantum physics is already impacting our lives in some pretty incredible ways.
Okay, so beyond the supercomputers and unbreakable codes, where else does this lead us?
Well, how about sensors? Imagine a sensor so sensitive it operates at the level of individual atoms. We're talking about detecting the tiniest changes in gravity, magnetic fields, even individual molecules.
Wow. What can we even do with that kind of sensitivity?
The possibilities are mind-blowing. Think medical diagnostics. Imagine being able to detect diseases like cancer at the earliest possible stages from a single drop of blood, or monitoring brain activity with incredible precision, leading to new treatments for neurological disorders.
That's incredible. It's like having a microscope for the human body that can see right down to the cellular level.
Exactly. And this is just the beginning. Quantum sensors could revolutionize everything from navigation to communication, even energy harvesting.
We talked about quantum biology earlier. Could quantum phenomena actually be happening inside of living things?
That's one of the most exciting frontiers in quantum biology. There's growing evidence that quantum effects like coherence and entanglement might be playing a role in processes we thought were purely chemical.
Whoa, 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 back up. What's quantum coherence got to do with biology?
Okay, picture this. Imagine a choir, perfectly in tune, each voice singing in harmony. That's coherence. Now, some scientists believe that the incredible efficiency of photosynthesis, how plants use sunlight to make energy.
Yeah, everyone remembers photosynthesis from school.
Well, it might be that this efficiency is due to quantum coherence happening within plant cells. It's like they're harnessing the power of quantum mechanics to optimize their energy production.
Plants are using quantum physics to stay alive.
Yeah.
That's amazing.
Isn't it? And then there's bird migration. Some birds can navigate across thousands of miles with pinpoint accuracy. Scientists are exploring the idea that they might be using quantum entanglement to sense the Earth's magnetic field.
So like a built-in quantum compass. That's wild. But with all of this potential, are there any downsides? Should we be worried about the ethical implications of all this quantum power?
That's a really important question. Like any powerful technology, quantum physics has the potential for both good and bad. We need to be having serious conversations about how to ensure responsible development and use of these technologies.
It sounds like we're not just talking about new gadgets here. We're talking about a fundamental shift in how we understand the universe and our place in it.
Absolutely. Quantum physics challenges us to rethink some of our most basic assumptions about reality. The idea that things exist in definite states, that information travels at a finite speed, these are all up for debate in the quantum world.
It's mind-blowing to think about. We're still just scratching the surface of what quantum physics can tell us about the universe.
That's the beauty of science, isn't it? The more we learn, the more we realize how much we don't know. And every answer leads to a dozen new questions.
Well, I'm hooked. This deep dive has been an incredible journey into the strange and wonderful world of quantum physics.
Me too. It's amazing to think about all the mysteries that are still out there waiting to be unraveled.
Exactly. So, to everyone listening, the next time you think about the world around you, remember that beneath the surface, there's a whole universe of quantum weirdness just waiting to be explored. Thanks for joining us on this incredible adventure.
Until next time, keep asking questions.